So welcome back, everybody. Let's resume the workshop. So this after lunch session will be started by one eminent member of the Links Scientific Committee, Marco Ajmone Marsan from India Networks and Politecnico di Torino. So we welcome Marco every year for very insightful talks. So I'm sure it will be the same today. So I leave you the floor.
Thank you very much. Good afternoon. I'll try to speak in a soft tone so you are happy, you are free to doze off, don't listen to me. So the topic I chose to tell you about today is the multi-server job queuing model. So I'll first try to explain why we are looking at this new type of queuing models, and then give you some results. Then at some point, when the time is over, I will stop. Let me just start my stopwatch so that I have an idea of whether I'm running late. Okay, so the main motivation for this type of models is data centers, which is not unrelated to networking, as you all very well know, since the trend of networking is more and more towards a set of interconnected computing centers, and this goes in the direction of what they call the computing continuum. And data centers have become extremely large, extremely complex, extremely expensive, extremely energy hungry, consume a lot of energy, consume a lot of everything. The biggest one are up to hundreds of thousands processors, extremely high cost both for operation and for constructions, and they serve a very diverse mix of requests. Jobs, which can range from scientific computation to training of large machine learning models, very diversified requirements in terms of number of processors, types of processors, because they can be standard CPU or GPU or hardware accelerators, whatever, amounts of storage, I/O modules, and so on. And what happens is that we essentially lack the modeling tools to study this kind of systems. And we lack tools because the traditional queuing models mostly consider just one dimension of service. So what happens is that every customer in a queue is granted a server, uses a server for a variable amount of time, and then releases the server, and you go on to the next customer and so on. So essentially, service in queues is one-dimensional, and the variable dimension is time. In order to capture the complexity of data centers, we would need models where services are multidimensional. So we would need an extension of queuing models which takes into account this multidimensionality, which we essentially don't have. We have very limited cases where you have a service that use more than one server, but the numbers are constant, you don't have a lot of variability, and so on. So this need has been realized by the scientific community, although still there are very few groups that are investing in this direction. And as for the time being, we start seeing some results for the two-dimensional case. The two-dimensional case, which is called the multi-server job queuing model. This is what I've been working on recently, basically with my colleagues in Venice. All of this started when I visited Venice for a period last year, and I started working with a group of very smart people, and we started playing with this multi-server job queuing model. What happens in this case? In this case, we have an arrival process, which we can take as Poisson, where arrivals occur one by one at a given rate that we can call lambda. And each job requires a number of processors. So the difference between jobs is not only in the service time, but also in the number of processors that are requested. Of course, you have a given total number of processors, which we typically denote by n. And every job that arrives is classified, and each class corresponds to a request for a given number of processors. Results in the literature mostly consider the first in, first out case, although in reality, data centers use very complex schedulers. If you are not in the data center domain, these names probably don't tell you much, but Slurm, Omega, Borg, Kubernetes are typical names. And you probably recognize Kubernetes because this is a typical resource manager that is exploited also in the domain of networking. So here you have an example, three possible job sizes. Jobs can require 1, 2, or 3 servers. The red jobs require 3, the blue jobs require 2, the green jobs require 1. And here you have an example where you have in service 2 red jobs and 1 blue job. This is a very lucky case because here you are using exactly the 8 servers that are available in your queue. Assume, however, now that the red job at the bottom leaves. What happens is that it frees 3 servers. These 3 servers are captured by the green job, but the green job only uses 1. And this means that you are left with the 2 idle servers, which cannot be exploited by the next job in queue. So you end up with head of the line blocking, where there is the red at the head of the queue, which is blocking the green, which is second, and 2 idle processors. This queuing system is not work conserving in the sense that you have jobs awaiting service at the same time when you have 3 servers, and this is one of the main complications for the complexity of the system. And this waste may have a severe impact on performance. The analysis is typically difficult. There are few results for corner cases. The case where you have the same exponential service duration for every job, or, well, of course, this can be modeled with Markov chain if you assume Poisson arrivals and exponential services. The problem is that the state space explodes pretty rapidly because you have to take into account all of the combinatorics of the different jobs in service. And also complex solution under saturation. Many aspects are interesting for this type of queuing models. Of course, what we would want is a simple exact analysis. This is escaping us, at least for the time being. We would like to have results for non-exponential service times. If we are not able to have a simple exact analysis, we would welcome approximations and bounds. And also, what is very important, it would be interesting to establish some general laws on the optimality of different schedulers. For example, in the case of traditional queues, we know that the optimal scheduling which is possible is the shortest remaining processing time first. We have no idea of what is the best possible scheduler in the case of 2 dimensions or more. So, in order to simplify things, several researchers, and we followed this trend, have been looking at the case in which jobs are only can only belong to 2 classes. So the request of the number of processors posed by jobs is variable, but jobs can only request either for just 1 processor or all the processors in the system. And so this is an environment which is called one or all, or big and small, and the probability that an arriving job is big, so it requires all of the available servers is PB. 1 minus PB, of course, is the probability that is small, that the job requires just 1 server. Service times have to be exponential for small jobs, the jobs that require only 1, whereas the results that I'm going to show you will be true for any distribution of the service time of big jobs. The workload is written as the arrival rate of small jobs times 1, which is the requirement in terms of processor for small jobs, times µs, divided by µs, which is the service rate of small, plus the arrival rate of big, which is lambda PB, times n, which is the number of requested processors, times 1 over µb, which is the average service time of the big. What is the stability condition of this system? Stability condition is not obvious. It is not, as you would expect, simply rho less than capital N. If this was an MMMQ, that would be the case. Here, what happens is that we are wasting resources because we are not able to use all servers. So we have head-of-the-line blocking, and so stability is not simply rho, the workload, less than n, the number of servers. What happens in this case, if you have either 1 or all, is that if you have 1 in service, 1 big in service, you are using all servers. If you have 1 or more small in service, you typically lose a lot of resources. This is the limiting case where you have 1 small job in service using only 1 of the available n servers. You have a big job which is at the head of the line, and you are wasting n-1 idle servers, which is bad in terms of performance. Turns out you can study this system. You can do a not so complex cycle analysis, because in fact what happens is that the system evolves in cycles, and these cycles comprise exactly 1 big job plus an arbitrary number of small jobs. Of course, this number of small jobs is geometrically distributed, and so you can express the average cycle time. The average cycle time has 1 average service time of a big job plus, according to the number of small jobs that you have these sums of 1 over I µs, one of the complexities here is related that the rate at which you are completing service of small jobs is proportional to the number of small jobs that you have in service. So you end up with these summations, and you end up with these curves. You end up with these curves, which are pretty interesting in the sense that here these two curves are as a function of PB, which is the probability of having a big job. At the far right, where PB is equal to 1, the behavior is trivial because this system is actually working like an MM1. You only have big jobs. Big jobs use all of the servers. So it's like having just normal jobs that use the only one available server. Same thing to the extreme left. To the extreme left, when PB is equal to 0, you only have small jobs. And having only small jobs means that your system is working like an MMM. So the two extremes are well known. The tricky part is in the middle. And you see that in the middle, you have a behavior which is far from just an interpolation of a straight line. And actually, you have significant differences depending on what is the average service time of big customers, and also depending on the distribution of small customers, of the service time of small customers. I didn't give you the expression, but in addition to getting the stability condition for the case of exponential distributions of the service times of small jobs, we also got it for constant service times of small jobs. And what you see here is that the deterministic case gives you a larger stability region than the exponential case, which you probably would have been able to guess altogether. But you also see that long service times of big jobs are less critical than the case of short service time of big jobs. Why is this the case? This is the case because you are wasting during the transition from small jobs to big jobs. Remember this that I was showing before. In this case, when you have a big job which is at the head of the line, you have to complete service of all the small jobs. Here you have the last remaining one, but you are losing during the period when you are transitioning from a sequence of services of small to a sequence of big. If you are wasting and then you're serving a big job for a long time, then it's not so critical. If you are wasting and then the service time of the big job is very short, then what happens is that your performance is bad. And this is what you see here. This is what justifies the fact that the brown curves are more or less grouped, whereas the blue, the green curves, where the service time of the big jobs is short, are very much far apart. And you also see that the amount of loss that you can have is fairly big just because of the head of the line blocking. Now, one important thing, especially in light of the application in the domain of data centers, is to come up with better scheduling policies with respect to first in, first out. And one of the things that have been proposed in the literature is, let's use a policy which is called most server first, which means let's not just choose the first one that is waiting. But let's look inside the waiting line, which is the best match for the amount of servers that are free. A job completes and you have some servers that are free. At this point, look within the waiting line and try to find the best one. Now, in this case, what happens is that you are bringing ahead, this is the case, again, one or all, but you are bringing ahead and putting in service whatever fits in service. And you end up essentially having no head of the line blocking. If you allow preemption, then stability is the best that you can do. So is rho less than n, like in the case when you just have an MMMQ. But the implementation can be complex. Why? Because you have to scan the entire waiting line, and the waiting line can grow very long. You end up essentially having a bistable behavior, because whenever you, especially when you are reaching saturation, you complete service of a job that is using K servers. What happens? You look for another job that requires exactly K servers. So you end up keeping serving always the jobs that have the same size. And this is especially true in the case one or all, when either you have a requirement of one processor or a requirement of n processors. You end up with a bistable behavior, and the system becomes a nightmare even to simulate. And for this reason, we tried to look for something simpler. And one policy that we defined is called small shuffle. The name comes because of the fact that it gives a nice acronym or something like that. We call it SMASH. And what happens in this case is that we don't scan the entire queue, but we scan only the initial W positions of the queue. This is an example of SMASH with window 3. You see you have window 3. In the window, you have two big and one small. The one small can be brought into service. If you bring this one small into service, you move everything ahead. Another small gets into the window, so this goes into service as well. And at this point, you cannot do anything else because the window is full of big. This is not a chance. You always commute from big to small and from small to big whenever you have the window which is full of jobs of the same size. And you can compute the stability condition. Now, I don't want to go into the detail. You get some more or less weird equations where you have to look at the expression. It becomes a little bit tricky. You end up with the regularized beta function and the generalized hypergeometric function. That is the detail. In case you're interested, I can point you to a paper. What happens is that basically you improve, but you are not really changing the game. You are doing better. You are doing better with reasonably small windows, but the difference that you have with respect to the theoretical curve here are the solid lines, and the solid lines is what is called lambda opt, and this is the case where rho is exactly less than n. So that is what you could, in principle, theoretically be able to achieve, but you are not getting there with small values of window. If you use larger values of windows, here you have the results as a function of the window size. You see that you have a diminishing return effect. Initially, you grow, but you don't get quite to the point where you have your theoretical capacity, which in this case are the dotted lines. The improvement is larger in this case for a small average service time of big jobs. And you see that the window helps, but doesn't really solve all of your problems. Okay, this is what we are able to do with analysis, but it's not really satisfactory because we are only considering jobs that require either one processor or all processors. That is not true in data centers. The situation in data centers is much more complicated. These are data from Google Borg data centers. These are extracted from this paper, which is a fairly recent paper, a couple of years ago, on measurements on some Borg data center. And here you see, here I have two different cells of a Borg data center, which are called cell A. Cell A are these three columns, and then cell B, which are these other three columns. And here, this column and this one give you the requirement in terms of number of processors. So you see that the requirement of the number of processors goes from 1 to 2,000, 3,000. And this is the probability, and these are the average service times. So you see there is a fairly large variability, both in terms of the number of requested processors and in terms of the average service times. The result are workloads with large variances. In particular, here the E of capital T means the average number of requested processors for cell A and cell B. E of tau A and tau B is the average duration of services in cell A and cell B, and the sigmas are the standard deviations. And you see in particular that you see, first of all, that cell B is much more critical than cell A in this case. And you see that the variance of service times in cell B is quite large. Well, here is a zoom of the results. You see that there is a very large number, a very large fraction of jobs that require just one core. And you see, look at the blue lines, that there are job classes that have very low probability, but long service times. So you have to be careful with what you're doing. This is the result for cell A. This is the result for cell A simulations with the actual workload of cell A. In the case of first in, first out, most server first that I described before, a smash with window 2, 5, and 10, and one more policy, which is called server filling. Server filling is a policy that requires preemption, and that tries to fit the jobs at the head of the queue inside service so as to optimize performance. The most important things here is to notice that in this cell, which is not a critical cell, the capacity of first in, first out is 76%, whereas with the server filling, you can go up to 99%. And you might say, well, okay, after all, not so bad. With the other cell, which is cell B, which I told you is more critical from the point of view of workload, the capacity for first in, first out is below 30% of the installed equipment. So you build your horribly complex, huge, extremely expensive data center, and then if you don't pay attention to your scheduling policy and you just go with FIFO, you are using your resources at 30% capacity. Ridiculously low. And you see that also a very good policy that implements preemption, like server filling, goes up to 86, 87%. So in any case, you are wasting 13% of your purchased and installed capacity. These systems have very weird behaviors. This is just an example of a weird behavior where you see the average response time, which has a non-monotonic behavior as a function of increasing load on the horizontal axis. On the horizontal axis, on the axis, you have the arrival rate, which means you are increasing load along the x-axis. On the y-axis, you have the average response time, and you see that the average response time is not monotonic. Why is this not monotonic? Well, this is not monotonic because of those stable behaviors I was mentioning before, essentially. But it's pretty weird, and these models are full of these kind of surprises. So, as I said, real data centers use very complicated schedulers. These schedulers are designed empirically. They are designed by very experienced people who know what they're doing. I'm not claiming that they are not designed in a reasonable manner. What I'm claiming is that we don't have theoretical results that can somehow guide the design and suggest improvements. What we are trying to do is to understand the laws that govern the behavior of these kind of systems, which are extremely complicated and kind of addictive. I mean, since I started working on these things, I barely have time to think of something else. And if you find this interesting, please let me know. There are very few groups working on this subject. Research on this topic was essentially started by Professor Moore Harcourt-Balzer and is carried on by a number of her PhD students. In Europe, that I know of, there is only the group in Venice with which I am cooperating. But I think this is a very good topic for research. If you're interested, please reach out. We would be really happy to talk with people about these kind of problems. Thank you very much.
Hello. Yeah. Okay. Thanks for the nice lecture. I have a couple of questions. The first one is the case where when you have small jobs, they decide of servers. You have to be served by server 5 and 7. No, in this case, it doesn't, because in databases there were problems of this type where they say you do the updates of certain things and on certain data which are only on certain servers. And
no, this is one additional dimension in the sense that it may very well be the case that not all servers are equivalent.
Yeah, right.
But we are not there yet. In our case, all servers are exactly the same. So any requirement can be satisfied by any server.
Right. Okay. And the second question, I mean, things seems to be very much linked to the FIFO assumption. If you would go to a generalized processor sharing, I mean, where the part of the speed, of course, depends on the number of servers that you that you use, right? Would there be ways for other disciplines of having some sort of general processor sharing model where you would really, I mean, share the load or the capacity through everybody at the same time?
Yes, this does not yet guarantee that you are able to use all of your processors, because there can be combinations of numbers of processors, or depends also what are the resources. The next reasonable case that we have started very recently to look at is the case when you have processors and memory. But in order to enter, you need to have a given number of processors and a given amount of memory. And you are never guaranteed that you have in your hands a group of requests that is capable of completely filling the processors and the requests that you have. Then you can do time slicing, which essentially goes in the direction of processor sharing. You know, this has similarities with the knapsack problem, because you are trying to fit these things in an available space, which is essentially an infinite rectangle with a given width, which is the number of processors that you have, and you have to allocate this along the time dimension, trying to be as efficient as you can. If you add dimensions like memory, for example, then it still is a sort of a knapsack problem, but your knapsack has 2 dimensions plus the time. And it's tricky to be able to perfectly fit whatever request you have into your knapsack.
Okay, thank you.
So very quickly, how does any of these policy affect fairness or throughput that is assigned to a particular class of job? And presumably it doesn't keep things constant. And so the next question is, would that then possibly be used by users to decide that, I'm not going to be sending jobs of that size, but I'm going to be changing my size so that I can get a better throughput?
Yeah, sure. The point is also that some of the schedulers request users to specify different characteristics of their jobs. So they ask you to specify how many processors you want, how much memory you want, how long you're going to run, and so on. And this affects the results of the scheduler, because the scheduler tries to fit these things as well as possible according to what you declared. The key point is that, one, even trying to be as honest as possible, you probably are not able to provide very accurate estimates of what your job is requiring. Second, you immediately open the door to what you're saying. So I immediately start to try and inferring what is the best declaration in order to improve my performance. And yes, this is critical. And this is one of the reasons why we are trying to work with policies which are blind to other requirements except the number of processors, which typically is something that the user needs to specify because you want to run on so many cores. Interestingly, one thing you hinted at, which is I could group, grouping requests, saying, for example, everybody who asks less than 8 processors, I give him 8. Everybody that requests between 9 and 32, I give him 32, and so on. For starter, you would say, gee, that is really stupid because you are wasting a lot of resources. You are giving 8 to a guy who wants 1, so you are wasting 7. Believe it or not, at the end of the day, when you do the computations, you are more efficient than giving to everybody exactly what they want. Why? Because you are filling your system much more efficiently. There was a question up there. I'm afraid that throwing the thing, someone is going to get hurt.
Thanks a lot for the talk. I just want to say that we are working actually with a student from Polytechnic of Turin in the scheduling problem on Kubernetes. And one of the things that I liked is the analogy with the knapsack. But the problem is that in this particular case, the problem is also topology dependent, in the sense that not all sequence of CPUs are the same. There are some CPUs that need to be accessed in a specific sequence. It's also topology dependent in the sense that some CPUs work better together, like in the example in slide 9, different, if a job is across different NUMA nodes, for instance, they are performed in a different way. And the last thing is about the uncertainty of data center networking. There are lots of what we call the link entropy that enters into the game. And by the way, there is one paper on Infocom 2024 where we address only the uncertainty part of it. But the other, it's really difficult to actually keep modeling this kind of system where the example, the processors that you were sharing, they are not all the same.
Mm-hmm. Yeah, actually, this is more complex than the basic knapsack. Also, because you cannot allocate freely. A job can be allocated only after it arrives. You cannot allocate resources that you had in the past. So it's really tricky. I'd appreciate receiving a copy of your paper. Thank you. Thank you very much.